So let me start. You see, the title of my there is a question mark in the title, and the answer is related fluctuations. So wait. So first, I'll tell you briefly what do I mean by fluctuation. Then we shall discuss fluctuations in BC phase, and then we take concrete example of this antiferromagnetic material, and then I'll calculate fluctuations for a smeared phase transition with material, and then I'll list my numerical results and conclusions. Sorry. So, fluctuation is simply just a dispersion of any physical quantity, and it is a deviation from its average value derived from many identical processes. This is just illustration for fluctuations. And in physics, fluctuations are very important. They say even Casimir effect is caused by fluctuation of vacuum, where the average electromagnetic field is zero. In some sense, you may classify fluctuations as normal and anomalous fluctuations. Here I bring the definition of fluctuations. If you want to calculate fluctuation of any observable, you just take its operator and calculate by this formula. Usually, fluctuation of any observable should be proportional to the number of particles. But if we represent it in this sense, then if alpha is zero, you say that the fluctuation is normal. Otherwise, you say that it is anomalous. And it is proven that for any stable system, the fluctuation should be normal. Now, here I bring some examples of fluctuations. For example, fluctuation in the energy is related to the heat capacity, and fluctuations in particle numbers is related to the isothermal compressibility, and the magnetization fluctuations are related to magnetic susceptibility. So usually all of these fluctuations are normal. So where we can hunt for anomalous fluctuations. Usually it's expected that you can find anomalous fluctuations in BC phase. A phase transition occurs exactly at the critical temperature, because at that point the fluctuation is maximal. But when you go outside of this critical temperature, then the system again becomes stable, and fluctuation should be normal. Well, here I bring just illustration. For secondary phase transition, you see the condensate fraction exactly becomes zero at critical point, but number of fluctuations has its maximum. And so when I studied literature on this subject, I saw that there is still controversy about the fluctuations in BC phase. On the one hand, Giorgini and his collaborators many years ago calculated the fluctuation in condensate phase, and then showed that in BC phase, number fluctuation, that is fluctuation of condensate fraction, is anomalous. And recently, some experimentalists from Denmark and Poland in some way experimentally showed that in BEC phase of atoms of rubidium, the fluctuation is anomalous. But on the other hand, Vyacheslav Yukhalov strictly mathematically has proven that there would be no anomalous fluctuations in BEC phase or even in normal phase. Now, in this book, we took just concrete example of BEC of triplons and calculated number of fluctuations. So, some years ago, Japanese experimentalists studied the magnetization Q of this antiferromagnetic material, and they observed that when you decrease the temperature, the magnetization goes down, and starting from some critical temperature, they start to increase. And this effect was explained by the BEC of triplons. Moreover, they show that the magnetization is proportional to the number of triplons, and staggered magnetization is also related to the condensate fraction of triplons. Then Japanese guys went on, and they measured even staggered magnetization. And unexpectedly, they found that the staggered magnetization does not vanish at critical temperature. It smoothly decreases after the critical temperature. And this means that this phase transition is not a second order. It is a smeared phase transition. Here I illustrate it. This is just, you see, this is the condensate fraction, and it does not vanish abruptly. It goes to zero asymptotically. In practical calculations, we use it Hartree-Fock-Bogoliubov approximation by using this effective Hamiltonian. In this Hamiltonian, psi is an operator of boson triplons, and mu is a chemical potential. Well, in such tasks, the chemical potential is given. It is related to the external magnetic field. And U is the coupling constant of contact triplon-triplon interactions. And for completeness, we added here exchange anisotropy and also Dzelashinsky-Moria interaction. And you know, this Hartree-Fock-Bogoliubov method is related to the mean field approximation. And in this approximation, everybody starts from this so-called Bogoliubov shift. That is, you just represent your operator as its classical value, that is a number, and plus operator of non-condensing particles. And all in all, you may in some way diagonalize your Hamiltonian and arrive to this grand canonical potential. In our case, it includes some variational parameters, for example, x1, x2, and rho 0. That is the condensate fraction. Well, minimization of this omega, for example, with respect to condensate fraction, gives following equation. Now this equation is very interesting. Just imagine that we neglect DM interaction. That is, we neglect this term. Now in this case, this equation has normal solution with respect to rho 0, and you may say that there is a critical temperature where the condensate fraction vanishes. But however, if you take account DM interaction, then in this equation, the rho zero never can be zero. And you see it is in the denominator. So you can say that we are dealing with a crossover instead of a sharp faster phase transition. So in practical calculations, first we just optimize our input parameter. These are coupling constants of interactions and critical magnetic field. So having fixed these values, we calculate heat capacity and fluctuations in magnetization by these simple formulas. Well, for second type of phase transitions, you know that heat capacity has its sharp maximum and has its discontinuity. So looking at the behavior of heat capacity, you can easily find critical temperature. But in our case, we have obtained this picture. You see, the heat capacity is smooth outside of some region, but it has something like oscillations near temperature. But this blue curve corresponds to the fluctuations of magnetization. That is the number of fluctuations. You see, it has got a sharp maximum somewhere. And well, I claim that this point, this maximum point, can be identified or interpreted as a critical temperature of this smear phase transition. Now I list my conclusions. First, there is no anomalous fluctuation in condensate fraction. At least in mean field approximation, condensate fraction is related to this number here. And it has no operator. And hence, its fluctuation is obviously zero. So the first conclusion there is that in BC phase, there is no anomalous fluctuation in condensate phase. And secondly, we have shown that the crossover phase transition, the heat capacity is smeared by the number of fluctuation which is proportional to the magnetization, to the fluctuation of magnetization has a maximum. And this point may be interpreted as a critical temperature crossover. Well, you know that in the nature there are a lot of smeared phase transitions and there are a lot of crossovers. So I think it would be quite interesting to study number or density fluctuations for smeared transitions, for example, such as BCS to BEC transition. And why? It will be interesting just to look if the maximum point of fluctuation will coincide with ordinary critical temperature or with T0, and just to compare. And moreover, there are some smeared phase transitions, magnetic phase transitions, are related to disorder. I think it would be quite interesting to study fluctuations in such materials, in such phase transitions, to look, do these fluctuations have maximum at some doping value or temperature? Thank you for your attention.
Thank you for your presentation. So my question is, so you prove that the fluctuation is maximum during the crossover for this exact material. And is that possible to prove that in any case, this crossover fluctuation is maximum. So it is possible to prove this by theory that. Yeah, this one.
Yes, we have shown that it has maximum. Well, in practice we show only for this case, but in general, frankly speaking, I tried by fail. In the future, I will try to do some analytical calculations. So I cannot do this while for a while.
But you don't know if it is possible.
I think so. If you use all equations, all instruments of thermodynamics, maybe it is possible.
Thank you.
Small question. What is the origin of the fluctuations?
Just come back to the definition of fluctuations. Well, the first origin at zero temperature is just under uncertainty principle. For example, between energy and time, between coordinate and momentum, and so on. At finite temperature, it is related to the temperature fluctuations. But you know, to cause some fluctuation, you should do something with this system. Just tickle it with something. In other words, you should make some random processes, just like throwing this coin. But actually, deep in my heart, I don't know. You know, in cosmology, they say that the reason of Big Bang is a fluctuation in vacuum. But who caused this fluctuation and how? God knows. I don't know.
In the case of second order phase transitions, when we have additional magnetic field, we also will have the same picture with smoothing. Is it possible to describe your effect as the existence of some kind of additional magnetic field?
Yeah, I think so.
Yes?
I think so,
It's
yes.
some kind of additional
Yes.
field which means additional fluctuations.
Yes. Yes. This is just this will look just a little bit exciting of the system, just tickling it.
Professor.
Yes, very interesting. But since the fluctuations come from a physical measurement situation, right? Then let's say even if you go down in temperature, and let's say you measure the magnetic field in a squid or in any system.
Please speak more slowly.
Yes. Oh, sorry. I'm sorry. When you make a measurement, let's say in a squid, and you go down in temperature, for example, there is no guarantee that there are no fluctuations in temperature. In fact, this is quite normal because your cooling is not a perfect curve. Although you average out this, but you're always in constant fluctuations. And if let's say you put a current to determine a transport physical property,
Yes.
and while you have resistance, you are changing locally the local temperature, at least in some areas of the sample, for example. So that in essence, the three equations you showed, which affect these fluctuations, temperature is the most important parameter also, always.
Yes,
So
I
this
agree.
would be one aspect, I guess, that would cause fluctuations in most measurements.
Yes, I agree with you. But you know, on the one hand, if you want to study number fluctuations, you should make identical random processes. For example, those guys who made experiments with BC to study fluctuations in condensing phases, they constructed many clouds of BCs, identical clouds with the same temperature. And then after some flight up, they just counted, as I understood, they just counted the condensate fraction. And they saw that there is a deviation from the average number, like here. But you're right that you cannot neglect temperature fluctuations.
Thank you very much.